My name is Matthias Langer, and I want to tell you a few things about real estate classification using SparkML. So before I get right into the details, let me just present the company I'm working for, which is called Irion. It's a software and consulting company based in Vienna, and they have greatly supported me for preparing this talk for this conference. As I was already saying, I will talk about a real estate classification using Spark. So before we get into the implementation, let's first look a bit at the actual problem I was trying to solve here. And in fact, for the last few years, I worked for a kind of a startup called TopRop. And the idea behind TopRop was to have a single web page where you can find all the real estate for Austria, so that you no longer need to go to many different websites if you're looking for a new flat or for a house or whatnot. And yes, as with most startups, I guess, it didn't work out so well in the end. And I really can only sign everything that Rory said in the morning about startups. But as also with all startups, we all learned a lot, and a part of the things I've learned, especially from a technical standpoint, I will present here today. So as I've said, our objective was to have a single meta search engine for all the real estate property in Austria. And to implement this, we of course needed some generic web crawling technology that then would get all the different adverts from all the different sources, and finally write them to a search index so that we could then present it in our GUI. And in this whole crawling pipeline that you can see here, one of the first steps after the HTML had been crawled was to actually classify the crawled content. You see there are some other components here in this diagram. For time reason, I will not talk about them. Some of them might be worth their own talks. But here I will focus on this classifier component, and all the rest I will leave out. So here is, let's look at this in more detail so that you really understand what's the problem here. So here you see some random real estate adverts from different sources, and then the actual the task of the classifier was to then say, okay, this first one is residential, it's an attic flat, and it's out for rent. And then the second one, maybe it's a commercial listing, and it's actually a premise, and you need to purchase it. And then the third listing you see here, actually it's not a flat at all, it's a car. And since we are not interested in car, for our perspective, this then would be labeled as spam. So the class structure, let me take a brief look at the class structure, which is like the output of this classifier application. We have you can see 3 different axes. So there's for one the property type that can be residential, commercial, or miscellaneous. Then there's the property subtype. That's what you might all think about. This is stands for things like apartment, attic flat, premise, office, store, and so on and so forth. And then last but not least, there is also the listing category. There are just 2 possible values. One is rent and one is purchase. And the task of the classifier was to correctly, of course, assign all of these 3 classes to each HTML listing that it processed. And of course, if you do machine learning, one of the first things you need is some training data. And since for us Mechanical Turk was not really an option for legal reasons, I had to in the end implement a little application just for collecting this training data. So we hired a few students that then would all day long label real estate adverts. And this actually was a major effort of its own, so you shouldn't underestimate this. It, I guess, took me about a month to come up with some prototype that was then refined over the time. And also, and we had this in from the very start, you really should have some verification. So you should never trust just a label, a manual label from a single user. So in our system, for a classification to be later accepted into our training data set, it was required that at least 2 different users classified the listing identically. And in fact, there are cases where like 6 different people classified one at the same listing differently. So this is not something that is optional. You should really do this. So finally, I came up over the time with some 48,000 labeled examples that I could then use to train and test my algorithms. And I used about 38,000 of these examples for the training, and about 10,000 of these examples for testing how well I'm doing. You already saw these 3 different kinds of axes, like the property type, the property subtype, and the listing category. And if you would like now look at all possible combinations, you would end up with a value like of 150 or maybe even more. But in reality, not all of these combinations really make sense. So you won't have a residential office, for example, unless you really want to live in your office, but normally that should not happen. And so in total, we had like 42 effective labels that could be found in the data. And something that's that also comes, I mean, from the way the data is out there in the world, is that, of course, this data set was very, how do you say, unbalanced. So we had about, or in this data set, there's about 19% residential apartments for purchase, but for example, 0.1% garage purchase lease. This is just because like in the real world, there are some types of properties that are very common and other types that are far less common. Yes, before you start evaluating any machine learning based classification, you should look at the so-called baseline accuracy. So for example, if I just used a random classifier, what performance would I get? So here, if I just would label my real estate adverts randomly, I would still get a performance or accuracy of 2.5%. If I just said, okay, there is this majority class, 19% of all the stuff I'm getting is actually apartments for purchase, then I would get a accuracy of 19%. And finally, I also looked at performance a human could get. And surprisingly, this performance also is not as high as I would have initially expected. So you see here that it ranges from 92 to 96%, even for a human looking at the data. And yeah, this comes in fact from the problem that in reality, if you look at real estate listings, using such rigid classes often does not very much reflect the true nature of these listings, because very often you have an advert that in reality just contains, it might be that they built some new house somewhere, and now they have maybe a premise in the basement, and then they have a few, I don't know, normal apartments in the 3rd and in the 4th floor, and then finally on top they have a nice penthouse. And this might be all in one listing. And so for people doing these manual classifications, sometimes it's really hard to decide, okay, how should I really classify this? Because there are like competing informations. Actually, this should be in multiple classes. And so in retrospect, I have to say that it would have been much better to use tags. So we could have said, okay, this listing has the tag apartment, and if there is also like, if for example, this is very common that an apartment can also be used as an office. And if the apartment can also be used as an office, then it will also get the tag office, and so on and so forth. But since we started off with this rigid class system, we then had to define rules. So how will you finally classify an apartment that can also be used as an office, and so on and so forth. And this made it, in the end, harder for humans to do this manual labeling for the training data, and then of course also harder for the computers to learn what these rules really should be. So if you're by accident at a similar stage as I was back 2 years ago, and you're about to set up machine learning based classifications where you have to to find, or you have to like get organize training data, or it's like your task to get hold of some training data, really think about if tags wouldn't be the smarter solution, because they might actually be more easier to deal with by humans and by computers. And still, if at the end you want a rigid class structure, then you just could define some hard rules in maybe some 20 or 30 lines of Scala code, which combination of tags then gets mapped to which rigid class. Yes, having said that, let's take a look at some implementation details. So as I already said, as the title already says, in fact, I used Apache Spark to implement this. And in retrospect, I'm not sure if this was the right solution, because Spark is really, I think, a great technology, but it's mostly focused on big data. And for the problem I was working with, all these nice big data features were not really needed. But of course, they bring in a lot of complexity that I still had to deal with. So my advice, if you are maybe at an early stage in your project and you're thinking about should I use Spark or should I not use Spark, really think about the amount of data you're going to deal with. And if you find out that it's only a few gigabytes and it might easily fit on your laptop, maybe you can go with something simpler. Anyway, we use Spark, and and if you want to do machine learning with Spark, then you will very soon find out that inside Spark there are actually like two packages, both offering you machine learning, both implementing machine learning algorithms. There's this mlib package and there's the ml package. And this also caused some confusion to me in the beginning. And of course, as things go, if they go wrong, they go really wrong. I started using the mlib package first, only then to later find out that the Spark ML package is the better one, the newer one, and that Spark mlib will eventually also be removed, I think, in Spark 3.0. So the basic difference is that the Spark mlib package is based on RDDs. We already heard about RDDs in the last talk, I think. And the Spark ML package is based on datasets that itself are also based on ADDs, but they are like a higher level API. So if you remember anything from this slide, just remember, stay away from mlib and use ML if you're doing machine learning with Spark. So if you take a look at the classical classification pipeline, or at the classical text classification pipeline, at the beginning, of course, we have some text, some HTML, and this text then has to be converted, of course, into feature vectors, which are just in the end vectors of floating point values. Then we might transform these features, then feed them into a model. That's a model that we might have, that might come from some machine learning algorithm that has been trained on our training data. And then hopefully this model will then finally give us a classification that makes sense. So I don't want to give you an introduction into Spark ML here, because this would, I guess, need several presentations. But just so that you have a brief overview and we're all on the same page, the architecture of Spark ML is, you could say, based on this notion of pipelines. So a pipeline can contain either transformers or estimator. A transformer is really just a transformation, as the name says. So you give it a data frame. A data frame, you can, if you have never heard of a data frame, you can think of a data frame just of a distributed, of a potentially distributed table of data. And so it gets a data frame, and then it applies whatever transformation, and it returns you a new data frame. So that's all the transformer does, basically. An estimator, on the other hand, can't do transformations of its own, but you can give it a data frame containing some training data, and it will then give you back a model, which is itself a transformer, and might do some transformation based on the exact algorithm and the training data you gave it before. So an estimator can be sort of an like abstract machine learning based model. So it might be, for example, logistic regression estimator, for those of you who have heard about logistic regression, and then you give it the training data, and then you get back a transformer that hopefully will do whatever it was trained for in a reasonable manner. So let's maybe look at some more concrete code examples. So how this actually looks in Spark. So here I'm constructing a pipeline, and here in the first row I just have like the feature extraction parts of my pipelines, where I have this terms extractor. The terms extractor basically takes in HTML and gives me back terms. You can think of terms just as the sequence of words in this HTML, or if you want to be a little more fancy, also as the sequence of n-grams. So you take the two adjacent words, and you can add them too. I will explain this later in more detail. And then, of course, as soon as you have these term sequences, you need to project them into like a real valued vector space to get feature vectors that your algorithms can work with. And this, for example, can be done with this count vectorizer you see here. That's also like a component you don't have to implement. You don't have to implement yourself. Spark will do that for you. So the count vectorizer will then basically assign a dimension to each of your terms, and using this mapping of term to dimension will just map this into the real valued vector space. And then, as we saw on the slide before, we might do some transformation to our features. So, for example, almost every English document will contain the word "and," will contain the word "of," will contain the word "in," and most likely, or in most cases, these words are not very relevant to the content of the document. Whereas other words that are very specific to this document, that only appear rarely in other documents, or almost never in other documents, might tell you very much about the actual content. So to account for that, what's often done is some additional transformation where you weight down these very, very common terms that are often also called stop words, and you emphasize these rare words that are more relevant to the topic content. Yes, and as soon as you have these transformations together, you can then like construct your full classification pipeline by just plugging this all together. So you take the feature extraction, then you add the feature transformations, and then of course this all wouldn't make much sense. You also add the actual classifiers for the different axes, or for the property type, for the property subtype, and then for the listing category. And these classifiers here, of course, they are machine learning algorithms and need to be fit to some training data. And this is what is done in the last line. And so then this Spark will be intelligent enough to fit all these different stages in this pipeline one after the other, so that when you finally get back your pipeline model, you can really put this to work and it will actually do the classifications or whatever you trained it for you. As I've said, the classifications or the classifier application I'm presenting here is based on this bag of Ngram model. I know that this is not the most sophisticated model. There are like very interesting things like paragraph vectors, but they are not part of standard Spark. So I didn't look into these, or also I didn't finally have much time to look into this. But anyway, this bag of Ngrams, in this bag of Ngrams model, so if n is 1, then bag of Ngrams is just bag of words. So you have whatever text document, and you take all the words and you put them into a bag. And after that, you have lost all the information about the order of these words in the document, and you only know, okay, maybe the word flat appeared 3 times, maybe the word floor appeared 4 times, maybe the word and appeared 15 times, and so on and so forth. And if you want to account also a little for the order, you can add bgrams to these unigrams you've added before. So here's a simple example. Let's say we have the sentence, the cat ate the dog. And so then if we just did this Ngram transformation with n is 2, so then we would have there itself is a unigram appearing 2 times. Then we would have that dog. This is actually a bgram appearing 1 time. Then we would have at there appearing 1 time, and so on and so forth. And of course, you could do this with any n that makes sense to you, but normally the values of n will be rather low. Yeah, then something else I did this to improve the performance of these of my classification algorithms was that I introduced so-called interval tokens. So if you look at real estate adverts, you will often find text like this flat is 45 square meters and costs 35,000 euros. And if and here I would then replace the 45 square meters with this synthetic interval token that just then tells me, okay, there's a square meter amount between 25 and 50, and I would replace the 35,000 euro you can see here with another interval token that just tells me that there's some euro amount between 250,000 and $500. Why am I doing this? I'm doing this so that if there is another flat, maybe with 46 square meters for $351,000, so that this will immediately look similar to the models. If I would just use the raw tokens, then at least in the beginning, you're looking at these feature vectors, this would like look two completely different things. And by using this kind of transformation, I'm helping the models to better detect the underlying structure. Something I'm also doing before I'm actually building this bag of Ngrams and transforming them into feature vectors is that I remove some parts of the HTML that are often misleading, like link texts, and I've indented and footers and headers and stuff that usually don't contain much information, but in some cases actually could be misleading. And yeah. Another thing I'm doing, we already talked about this a bit, so I will be very brief on this, is that I'm applying these feature weights. So like very, very common words will be weighted down, so they will get less importance, and rather rare words that only appear in a smaller number of documents will get more importance. And the most, the best known transformation that accomplishes this is called the inverse document frequency transformation you see here. And that's also already more or less built into Spark, so you don't have to implement this yourself. So here is some some table that actually shows you how these different transformations and tweaks actually what influence they had, and how well they worked, or what difference they made. So let me just explain this table to you briefly. So here on the right side you see the total error for different combinations of these term extraction settings, and you see that the best value we get here for the error rate is 9.9%, and there I use like I use bgrams. I have this HTML cleaning I just talked about enabled. I have these feature weights, these EDF feature weights enabled, and I have these range tokens we talked about before also enabled. So in this case I get an error of 9.9% on my test data. And now, for example, if I would just say, okay, let's disable this term weighting and see what happens, then I would get an error of 10.7%. So you see that this really makes a difference. And here on the other hand side, you see the error just for rent purchase. So as I told you, the classifier is in fact doing 3 classifications with property type, property subtype, and listing category. And listing category, this is just if this listing is rent or purchase. So if we get this wrong, this is really bad. If we like classify an attic flat for a normal apartment, it might not be ideal, but it's not a big problem. But if a listing that's for rent gets classified as purchase, that's really a bad error. And luckily, the error rate here is quite low. And you can also see that, for example, if I disable these range tokens, then the error rate also it's still low, but it will increase significantly. So these range tokens really make a difference here on this side, while they're not making such a big difference here when we just look at the total error. So yeah, if you look at the table like this, we might think, oh, that's great. Let's just build tables like this on our test data and then decide which tweaking or which parameters or which tweaks to apply. And this is something, in fact, you should be very careful with, because normally when you do machine learning, you work with a train test split. So maybe 75 or 80% of your data will be used for training, and the remaining 20% of your data will be used for testing. But as soon as you look at different configurations for your algorithms and then compare the accuracies you get from these configurations on your test set to decide which configuration to actually use. When you start doing this, your test set suddenly is no longer a test set, but it becomes part of the training set. And if you want your test error to give you a meaningful approximation of your real error, you should really avoid this. So what you should do actually is to further split out the part of the training set that is usually called validation set, and then you can try out all these different tweaks and combination of tweaks you want to evaluate, and then you can pick the combination that works best on this validation set. And after you have this combination, you can use exactly this configuration to retrain your algorithm again, this time on the whole training set, and then you can finally evaluate your error on the test set. But you should never use your test set to design how to configure your pipeline, because then your test set is no longer a test set. And luckily, SparkML provides APIs to help you doing exactly this. So here we can see there's this simple pipeline we saw before with the terms extractor, count vectorizer, and then here at the end we have this property type estimator. And then we just built a grid of all the parameters we want to try. So here I want to see what happens if I enable and disable the HTML cleaning. And then here I want to see how if I should use unigrams, bgrams, or trigrams. And then there is this class called train validation split. And I can just give this parameter grid to this train validation split class. Then, of course, this train validation split class also needs a way to know if like one configuration or one configuration was better than the other. So it needs a way to evaluate these configurations. So it needs an evaluator. This is like also built into Spark. It has a variety of options that I will, however, not talk about here. And then you can just give this train validation all your training data, and it will do exactly what we talked about. It will try all the different parameter combinations, evaluate, for example, the accuracy, and then finally pick the best combination of these parameters and return you the tuned pipeline. Another thing you can do using exactly this this train validation split class is hyperparameter tuning. So usually when you work with machine learning, your algorithms have some hyperparameters, and only in the rarest cases, I think, the default values of these hyperparameters will be the best values for your problem. So, for example, the logistic regression classifier in Spark has the two hyperparameters, regularization param and elastic net param. The regularization parameter basically adds a penalty for large feature weights, and therefore this is a way to, if you have heard about it, to prevent overtraining. And using this train validation split, you can, as before, just build your parameter grid and then let this implementation pick the best hyperparameters for you. And this is also something you should not forget about. As I said, the default configurations of these hyperparameters in general won't be ideal. So in my case, if I don't do any hyperparameter tuning at all, I get an error rate for about 13%. And with this hyperparameter tuning, I get 9.9%. So this really makes a huge difference. So you should not forget about it if you do machine learning-based classification. Last but not least, sometimes you might also be interested in comparing two different algorithms altogether. So you might want to compare logistic regression with linear support vector classifier. In that case, you cannot out of the box use this train validation split that Spark provides, because this train validation split only lets you define a set of parameters it should try out. But you can work around this by defining like an estimator that based on a parameter will like implement the one model or the other model. And as soon as you have such an estimator, you can also use this whole framework to select which algorithm might be best for your problem. And yeah, I don't want to go into details here. You can find this on Stack Overflow. That's a question. And also these slides are on GitHub, so you should have no problem to find the link if you're interested. Yes, so that's basically all I wanted to tell you about. So let's summarize this a bit. So first and foremost, if you're at the very beginning of your project and you don't know yet if you want to use Spark or not, think about it carefully. Spark is a very nice piece of technology, but it brings in a lot of complexity. And if it turns out that you don't need the complexity, you might be better off with a simpler solution. If, however, you choose to use Spark, stay away from mlib. Unless you have to. There are some things that might not be implemented in ML, but mostly ML already has all the features of mlib and even some features more. So you really just should use Spark ML. And also, if you're planning to train a classifier, carefully analyze your data and think about if it might not be smarter to use tags. It might really depend on your use case, but this is of all these things I'm telling you here, this is the one advice I really would have loved to have had 2 years ago. This would really have made a difference, I think. If I had used tags, I think I would have get better results, and also the people who did the manual labeling would have a much easier work to do, in fact. Also, applying domain knowledge never hurts. With applying domain knowledge, in my case, I'm referring to these range tokens and also to the HTML cleaning. And yes, hyperparameters make a difference. The defaults, at least in Spark, will most likely not be the best values for your problem. So you should really tune them and see what's the best value for you. And of course, above all, enjoy yourself and have fun. So, are there any questions?
How you deliver your ready-to-use models to production?
Well, actually, after they have been trained, I store them in a database, and then in production, when the application boots, it will just load the already trained models from the database. Does this answer your question?
Have you tried MLeap, for example?
No, I'm using ML, and ML actually provides all these saving methods already out of the box. For me, the problem was just that with ML, you can just save to the file system or whatever you have. And for me, for my practical application, it was much more convenient to store this in the database. So what I ended up doing is I saved it to the file system. Then I packed it all in a tar xz file, and I wrote that tar xz in the database. And for loading the model, I did the reverse.
Thank you.
First of all, thank you very much for a great and interesting tech talk. And my main question is about the Spark. Have you thought about any alternatives? And if so, what was your main concerns?
My main concerns with Spark?
No, with alternatives, because in the beginning you said that.
Yes, maybe there are quite a few things, quite a few Python libraries, I guess. And my concerns with them, I guess, were mostly that they were Python libraries, and that I'm not so comfortable with Python. But yeah, like scikit-learn, for example, or I mean, when I started this, TensorFlow was, I think it was out, but it was really brand new. But scikit-learn was already well established, and maybe I could have used this. But then I would not be standing here giving a talk on a Scala conference.
So in your analysis slide, you were showing the error rates, and you said you got the error rates for determining whether it was rented versus for sale was very accurate versus the general classification.
Yes.
Is it worth then dividing into two sets using that initial classifier, or does that just muddy the water? Could you divide it into and analyze it into rental versus
you
purchase?
think I could like first divide into rent and purchase, and then use
then train your classifiers on
the
subsets to
yes,
get
that's something I did. I mean, not with this distinction, but in the very beginning when I started the project, I had a whole cascade of classifiers that would partition into commercial and non-commercial listings, or into apartments and non-apartments, but this turned out in the end to be really complicated, both to optimize and to reason about. So I actually it was quite a pleasure to get rid of almost all of these classifiers, deleting a lot of code, and have a much simpler structure where I just had basically 4 4 classifiers, one for spam, yes, no, one for the property type, one for the property subtype, and one for the category.
Cool.